Hello guys. So after a long time, today we'll start something new. I thought we'll take a small break from sensing and start with the basic electronics. So we are going to start with the analog electronics and learn some basic concepts like transistors, capacitors, resistors, some things that you might have known, some things that you might have not known. So without much further ado, let's just begin. The simulation will be done in the multisim software. I highly recommend you to download it if you have not done so already, and just practice the circuits that we are doing in these sessions. Also, something that you might like to make from your uh, own problems. And yeah, I guess we'll have a lot more fun. Stay tuned. Okay, guys, so let's begin. Let's start with some of the basics of this simulation software. So this is Multisim developed by National Instruments, and it is a high-end product from containing all different types of libraries that have different components. As you can see, we have capacitors, we have inductors, MOSFETs, switches, LEDs, monitors. We have some digital components, some logic bits, terminals, sockets, you name it, BJTs, op amps. So we have a lot of different components that you can play around with, and this is another list where you can sort all of them. So you have the sources, basic, diodes, transistor, analogs. So I hope that you will find time to explore through all of this. We'll start with the very basic sources, and within that we are going to start with the power sources. So let's begin with the most basic component of any circuit, that is power. There are two types of power, as you can see, AC and DC. We'll focus first on the DC power. Now, as you might know from your physics class or from any other place that you might have learned, a cell or a battery consists of an electrolytic circuit where we get two different poles of the different polarities. One is called cathode and one is called anode. We are using similar kind of arrangement for the battery here. For our reference, we have set it to 12 volt, but you can also change the value to 5 volt. And you can name the battery anything that you may like in the label section. Let me name it battery. So yeah, the thing about multisim is that you can play around with such components, name them, and also simulate different kind of scenarios. Let's make very basic circuit using an LED, a resistor, and the battery. Now, if you may have used hardware before, or you may have interfaced in either any of the projects from our sensing videos, you might know that LED cannot be directly interfaced to battery due to the high potential from the battery. So generally, we let's try with the blue one. So this LED is the blue LED. You can select anyone that you may like. So let's try turning on this LED without using any resistor. Now, as it is a simulation, nothing much will happen. But in real life, the LED will certainly be burned. Now, as you can see, the LED is on. But in the real world, you should always add a resistor. So as you might know, a resistor is nothing but a resistive component of a circuit that can modulate the current flowing through a particular part or a section of the circuit. What a resistor consists of is a certain arrangement of inductors that only allow the particular amount of current to pass through it at a certain time. Now, there may be many different types of resistors, wire bound, there can be the different carbon based, many different resistors. Some are rated for higher ratings, so they may work well under high temperature conditions. Some are rated for high power capacity, so they may work well even under high power from high powered electricity. So there are many different kinds of components, and even within that, they may come from many different industries that may have their own specifications. For example, space industry may require high tolerance resistors, which are very accurate and do not have a higher range of error. Within each resistor, there is a certain margin of error. Say, if you want a resistor of, as we are having one kilo ohm, now this one might have an error of 10 to 20%. Here it is, the tolerance that we can set. So if I set the tolerance to be 10%, it would mean that this resistor will have the resistive element anywhere between 990 ohms to 1010 ohms. So yeah, in practical scenario, we will never have zero tolerance, but for our understanding sake, let's just keep it zero for now. Now let's start the circuit. So what do you think happens here? So this LED is not glowing now, and the reason for that is that the current required to drive the LED is not sufficient after passing through this resistor. Now let's try changing the value to say 0.7 kilo ohm and see if there is any change. Still no change. Let's do it one more time and keep it say 500 ohms, which is equal to 0.5 kilo ohms. Still no change. Now let's try something around 120 ohms. 120 ohms, 150 ohms is generally the uh, resistance that you will require to turn on a LED from a 5-volt battery. The reason for this is, as you might already know, the Ohm's law V is equal to IR means that the current required to drive the LED will be 5 volt divided by 120 ohms, which would be somewhere around zero point 0.5 or 5 milliamperes. So that is the safe current that you will need to drive an LED without burning it. So I would suggest always using resistors with your LED or any other display component that you may have. We are only using the 5-volt battery here. If we increase the voltage in the battery, say to 100 volts, again we need to increase the resistance or else the LED will be burned. Now if I keep it 1 kilo ohm, let's see what happens. As you can see, even at 1 kilo ohm, the LED burns, the LED glows. Let's try 100 kilo ohms and it is off. So somewhere around the range of 5 milliampere is the ideal current that you may require for turning on the LED. Great. So you know how to use the resistance the circuit, you know how to use the power source, and you know how you can interface a LED. Moving on, the next basic component in any circuit, if you want to simulate, would be ground. Ground is a very interesting part of any circuit. You always theorize the ground part. There is no actual grounding done in real life. Maybe in some three-phase connections or some other higher end devices, you use the ground pin to safely ground the whole appliance or some part of the circuit. What it does is that it takes any excess current present in the circuit and just connects it to, as you might have guessed, ground. So the ground pin is just there to discharge the device in case of any power malfunction, or if the devices which are generally made of plastic these days, but in earlier times the heavy metal machines were made of conducting metals. So to avoid the risk of having an electric shock, the metal part is just grounded to the earth, and so there is no case of a shock. But for simulation purposes, we require the ground to complete the logical part of the circuit. That is, the power will be the electrons will from the positive end of the battery and will go to the ground, and then the negative end of the battery will be connected to the ground as well. Now, let's explore. some other components and see what we can do. Let's take a switch for example. To start with, we'll take the simple SPST switch and let me just use it here. So the another great thing about the software is that you just have to drag and drop components and you can easily see the different ways you can interact with it. Let's try using this. So as you can see, the switch is right now not closed. So the circuit is open. When I close the switch, the circuit is closed and so the current will flow. It kind of works as a circuit breaker and you can manipulate the flow of current through using a switch. Let's see what else we can use. There are a lot of different components and I'm sure you will be very happy to explore all of them. Now let's see something different. Let's see a capacitor. So a capacitor is nothing but two plates between which some dielectric material is filled. It works as an charging discharging device which can be great to interface alternative currents. It can work in many different ways as a DC filter. It can work as you can say um, it works in many different ways. You can also use it as a capacitive element for sensing. You can use the capacitor for charging some discharge battery. You can use it as a slicer, as we will see ahead. You can use the capacitor in many different ways. The most popular use of capacitor is the RC pair, where you connect a resistor and a capacitor in a circuit. In many of the circuits, the RC pair is used to manipulate the say switching part of a certain elements. Let me show you how it exactly works. If you take for example this circuit, so another just before that, another basic component is a diode. Diode is nothing but junction of P and N type of semiconductors. I hope you may know by now what are semiconductors and what are PN junctions. Just as a recap, PN junctions are sandwich devices consisting of P and N type of semiconductors where they are continuously under the influence of the attraction of electrons and the electron hole pairs are generated. So not delving much into the theoretical part, let me show you. Diode generally works as a gate which will only allow the current to flow through one way. So you can keep in mind or you can think of it like one way highway pass, a sign that will allow only the traffic to flow through one way. It has many other uses like Zener diode. We can have other type of photodiode. As we'll explore, diodes are very useful these days, especially in terms of sensing and in terms of fast switching, and also the control of the flow of the current in the circuit. Not going much deep into that. Let's see. So this is an AC current source. I'm sorry, power source, which will give us 230 volt RMS, which is the root mean square value, and 50 hertz frequency. You can easily set this as the value that you may like. I believe in the states the regulation value is 210 volts, or maybe it is 120. I do not remember correctly. In India, the volt socket value for the voltage is 230 volts. What this means is that whatever place that you may are, the power generated is transported at 230 volts, not exactly 230 volts. The 230 volts is the RMS value. You can calculate the peak value, peak to peak value using the formula VRMS is equal to root 2 V times peak. But that is again something that you may not require at this stage. VRMS is, you can imagine, the amount of potential difference present in your whole circuit. So yeah, and the frequency is the rate at which the AC current is switching. So here we have 50 hertz. That would mean 1 by 50 at every 1 by 50 second the uh, polarity of the signal changes. I'll show you the simulation, I think, through which you will understand it better. Here we have a transformer. Transformer does nothing much except increasing the voltage and decreasing the current. So here we have a step down transformer through which we are modulating 230 volts to some lower value, which you can easily calculate by V out divided by V in is equal to number of turns on the primary coil divided by number of turns on the secondary coil of the transformer. So it's very simple. I'm not going again much into theoretical parts, and I'll just directly show you. Also, we have connected the ground here. We have connected the diode on the one end of the transformer, and the another end is directly connected to the negative part. In AC current, I hardly think there is a requirement for positive or negative. We are just trying to check what kind of signal you have. So let me stop the simulation here. So as you can see, the yellow part that we are having is the, let me scale it up. Okay, this is good. So yellow part that we are having is the modulated signal that we can say in a certain way. The black part is the original signal. This is a oscilloscope through which you can see signals on a screen. I would highly recommend you to check out cathode ray oscilloscopes, as they are going a bit extinct these days with the onset of digital oscilloscopes. But the conventional ones had more kind of analog feeling, and you could enjoy turning the knobs and just watching the different signals. So this whole part here works as a function generator, and our diode allows only the certain, sorry, our diode allows only the certain polarity. So let me explain. During the first cycle, say for example, we are talking about here, when the current is flowing, during the positive cycle, the current will flow through this red part. It will go to the diode and then move ahead. As the diode is in forward direction, the forward alignment, it will allow the current to pass through. Now, if the diode was in the reverse alignment, for example, and we'll soon try that too, it will not allow the current to flow in the back direction. So that we can consider as a one-way gate, as I explained earlier. And so only during the time that we are having the forward current flowing from red to the oscilloscope will the diode allow the current to pass. In the case of the reverse flow, say when the current is flowing from the this side, the orange part, as you can say, and the diode is as we can say grounded, it will not allow the current to pass through it. So as you can see here, in the negative cycle of the current, there is no uh, signal detected at the oscilloscope in channel A, as we can say, where we have connected this diode, and only the original signal will show a negative part, but our current signal has no negative part, only the positive circuit, only the positive part of the signal. This is something that we can call as basic slicing. We will not go into much detail on that, but what it does is that it cancels out the negative part of the signal so that we can easily work with only the positive signal. There are many different ways of doing this. You can either shift the whole signal a bit above, or you can just cut out the negative part, as we have done right now. What you have to understand basically is that the diode is in a particular condition wherein it will only allow the current to pass through one way. Now let's go back to our circuit. Let's see if we can design something like that. So let's see if we can take a diode. The standard diode for use is 1N4001, but you can choose any diode. It's not much of a big deal. And as I said, there are different types of diode. We have photodiode, protection diode, Schottky diode, and many different types of vector diode. So you can choose any of the diodes that you may like. Uh, let's keep the diode here. Let's connect it to the. I think we do not need the capacitor for this one. Let's just use it. I'll keep the diode here. Okay, before that, let me show you AC power source. So what are AC power sources? AC power source is something that generates AC power at the certain RMS and frequency that you have mentioned. Generally, the power source that we may see in natural states will be AC. It will not generally be in the DC form. So the electricity that arrives at your home is in AC state. The currents that are produced, I don't say current is not in AC or DC form. The voltage rather is in the AC form in all the natural uh, signals. And if you want to make it DC, then we will have to use different sort of modulations and conversions. A to D converters are present. And these days we have used many different techniques to make this conversion more efficient and more quicker. So let's see. Uh, yeah, as you can see, the LED is blinking as the direction of the current is flowing at 60 hertz from the positive end of the AC signal to the negative, and then in the next cycle from the negative to the positive. If I slow down the frequency, I think you will get a better idea. Let's do 10 hertz. So now the speed is a little bit more. Let's try some. Let's try 1 hertz. So at every 1 second, the polarity of the current changes. It goes from the positive to the negative part, and then again from the negative to the positive part. So I think this gives a clear idea of how the AC current source power source works. LED is also a type of diode, which we may name as light emitting diode, and as you can see, it will allow the current to pass through only one way. A better example to check on this would be a lamp, which will allow bidirectional flow of current and will glow in either positive or negative. You can say bias. I'll explain what bias is in just a second. Let me just search lamp. There are so many components here that you will love to explore them. So a lamp is not, uh, let's say it's not worried about what direction you pass the current in. You just have to switch it on, and just a second, I think I got the wrong lamp. So sometimes the components may not work because they have different specifications, and what I will suggest is the green colored components are generally reserved for digital and other kind of specific functions. So it is better that you may choose components which are in the black color. So for example, let's say this lamp, let's decrease the current value, sorry, increase the current. And if I, okay, so the lamp just broke. Let's try 1 kilo ohms, see if the lamp glows. Okay, let me decrease the voltage value to 50. Let's see, is it glowing yet? No. Okay, 20, and let's decrease the resistance to 100 ohms. Okay, let's try some different kind of lamp. Let's try this one again. We generally don't use lamps in demonstration. What we use is an LED, but I wanted to show you if it was possible to turn on this lamp. Let's switch it up to 120. No, I think it won't start. Let's see if we have something different. Uh, okay, yeah. So another great tool that we can use is a voltmeter. Let's so this is a multimeter which you can use to which you can configure it as a voltmeter, ohm meter, ammeter, anything that you may like. We can also measure decibels. So multimeter is a tool that will allow you to use many different components. What we are interested here is in voltmeter. So this will shows the reading the amount of voltage flowing through the circuit. As we have an AC signal, we are selecting the AC part. If we had a DC signal, we'll select the DC. So there is a difference in the sensing of the voltage, and if you do not select the AC component, then you will not get the correct reading. And let's see what signal we are getting. So yeah, in AC signal we are getting almost 120 volts. The rest of the 0.13 volts can be attributed, 0.03 volts can be attributed to loss of signal due to the resistor and every other component, which is the simulation is great because it has been mapped to the real life scenarios. Now if I turn it to DC signal, then it will give garbage value as it is in the reverse bias and not connected in the correct configuration. Now what is forward and reverse bias? Forward and reverse bias mean nothing much but the placement of your components. So say I have an battery and I take an LED. Let's try a green color. Now if I just connect it directly against my own device, so what will happen? The LED is flowing. Now this will be called forward bias as I intend to attach this part of the LED. Let me show you, try to see if I can extend this. Yeah, so when you are trying to connect the positive part of the battery to the beginning of the LED, I will say, and the negative part of the LED to the end of the negative part of the battery to the end of the LED, in the configuration that it is meant to be attached, it is called forward bias. Now what will be reverse bias, you may ask? Let me show you the reverse bias configuration. Let's rotate this LED and connect it in a different way than the last one. So I'm connecting the positive part of the battery to the negative part of the LED and the negative part of the LED to the positive part of the battery. Let's try. So as you can see, the LED which is in reverse bias condition, which is this one, will not glow. So any component kept in a certain condition, be it forward or reverse, is just the way it has been connected to the circuit. And I hope you got that. Now moving forward, we have the AC signal. So let's try using a diode. Let me show you the circuit altogether. Yes, so as you can see, let me show you the previous circuit once more. So we had here the resistor in parallel. You might be curious to know why was it. Let's try removing it and seeing what change in signal we can observe. I'll soon explain to you why the resistor was present. So as you can see, we have no meaningful modulation happening here. Instead, the signal is actually the reduced value of what we had earlier. Now, if I set both of the signals at the same scale and see what will happen, the signal is just getting very, you can say, small errors. Other than that, only the transformer is doing its parts. If I remove the transformer, for example, and connect the diode directly to the power source and the ground to the negative end, or say the other part of the AC signal, you'll observe that there is no visible difference in the signal. Let's simulate this. So, as you can see, let me set it at a readable scale, 200 volts. You cannot even differentiate between both of the signals. Now let's try adding back our resistor. So let's let me just pull up that resistor once more, and we can attach it. So what we are doing here is that we are connecting the oscilloscope in parallel to our resistor. Now what does parallel and series mean? Series means that you are connecting a component one after another, whereas a parallel connection means you are connecting both of the components with the same positive and negative part of the circuit, but via different appliances. So I think that you might get it. We are completing the circuit here in the resistor, and there is an additional component of the oscilloscope. Whereas in series, the connection was from the AC source to the diode to the oscilloscope, then back to the ground, and then to the AC source. Whereas here, the circuit path is something like this: AC source to diode to resistor to AC source, and then from the diode to the oscilloscope to the ground to the resistor, we can say. So this way we are connecting the system in parallel. We'll see series and parallel connections ahead of time, uh, but maybe in another session. Now let's run this once more. And as you can see, if I change the scale, it is clearly visible that, okay, let me just adjust it for a second. The colors in a way that you can see. We can stop the simulation. And okay, so now as you can see, the signal is sliced from the negative component and we are receiving only the positive part. Now let's try it with a capacitor. So what you understood what the role of a resistor is to connect the circuit in a parallel fashion. Some may even call this as a voltage divider network, but I prefer to use the term only when a resistive element is present. So let's see what a capacitor does. Now, as you can see, instead of having a wavy signal, we are having a certain DC slope which remains almost constant throughout the time. So what a capacitor does is that it acts as a DC signal generator here, and it converts the different modulating parts of the original signal, which is in the black here, to a straight line. So what is happening here in the actual circuit is that the capacitor, which is connected here in parallel, is getting charge and discharge every single time. Now the diode will only only allow the positive current to flow ahead, so as it is in forward bias. So by the time the current reaches the C1, either through this way or this way, it is only available in the positive part. Now the capacitor does not know which way the signal is, be it positive or negative. It will do its work equally for both of them. What a capacitor does is that it will flatten out the crest and the fall of the signal by using its own capacitive element. So inside a capacitor there are two metal plates or any conductor, and between them a sandwich of an insulator between two metal plates. It is kind of an NPN junction, and so transistors many times show capacitive uh, elements and may perform some functions, may show some errors that may arise due to these capacitive elements. Now, what it does is that it charges to a certain value. For example, here we have 50 Faraday. So this capacitor will charge till 50 Faraday and remain charged until the uh, ends of its poles are not kept at a lower voltage. So once the positive cycle ends, it will stop charging, and then once the negative part begins, it will start discharging, providing the oscilloscope with the same 50 Faraday or the same voltage, the potential difference that the wave was having. So you can kind of think it like a supplier. If you are providing it with some, say, 100 rupees per second, or say 10 bucks per second, it will take in the cash, keep 50, 60, whatever value you may set, $50, $60 per second with it. And once the inflow of the money is decreased, say you may be going through an economic crisis, it will supply back those 50, 60 dollars per second, and you can think of it as a storage device for potential difference or say voltage. It is a very useful tool in terms of you can exploit this charging discharging property to manipulate the switching and also converting AC signal to DC signal. If you use it in the reverse configuration, it can also work as a DC filter so that there is no DC component in your AC signal. Actually, when you are using AC components, if you pass DC signal through them, it will damage the appliance quite seriously. So it is really important to use a DC filter, especially in transistors. So I hope that today's session was a bit useful in terms of analog electronics, and I hope that now you can conduct some basic experiments regarding diodes, LEDs, AC/DC sources, resistors, multimeter. You can also use the multimeter as an ammeter. Ammeter is nothing but you can say visual representation of the amount of current flowing through a circuit. We can also someday look at the internal configuration of an voltmeter and an ammeter. It is a great discovery, and it has led to many different uh, breakthroughs in science and especially electrical engineering. So yeah, I hope this was an informative session. Uh, I would be glad to answer your questions if you may have any. Just drop down them in the comments. And till the next time, I urge you to do some real life experiments. So we had a lot of fun doing the sensing experiments, and I hope that you had the time and the energy to implement some of them. But for this, I really encourage you to go out there, take a breadboard, use some resistors, take a battery or any cell that you may have laying around and an LED, and try to run that LED with the power cell or battery that you may have. I will be really happy to know if you had faced any difficulties or if you did your own troubleshooting for these circuits. And yeah, I think the basic parts of this analog electronics can only be understood by implementing the circuits in real life. So I hope you will have a great time trying to learn through this hardware components. Till then, I guess just let's keep exploring. Thank you for watching this video and see you soon.